So I can start explaining a little bit how logical section are created. I will actually begin just with the basics of geological sections, so which are the principle behind the production of geological sections. But since I imagine that many of you already know this kind of basics, I put them a little bit in more planetary geological context. And even I have added some higher products, so some example higher level products like 3D models. So the first, one of the first geological sections ever done is this one from Giovanni Arduino in the 18th century. And it was actually done before any modern geological map, since William Smith had done the geological map afterwards. This is actually an interpretation of the slopes of a river in South Alps, in the Southern Alps in Italy, going from the Criston Basin to the left to that was called the primary unit to the sedimentary sequence that you see to the right, that named the tertiary, which is one of the epoch of the geological periods. So for this reason, actually, Giovanni had a dorsum on the moon called after him. So at the beginning, the geological section was just the interpretations of a field observations in the field without actually a geological map. With William Smith that we see here, the map again, now at scale, there is my wife for scaling reasons. And if we see here this tiny portion, we see the geological section by William Smith integrated to the first geological map. And we see clearly here that again, he is showing us very clearly the overlapping relationship between the different units. So there are stratigraphic sequences, and it also suggests a different inclination of the different geological units from west to east. Also, this kind of geological section is kind of conceptual because it's not so well constrained into topography. So, but we know actually that the distinction of geological unit in a planar view are actually the results of their distribution and their prosecution even underneath. So if we have a kind of classical evolution of a geological process, we know already that there is, if you want, position at the beginning, then we may have the deformation afterwards, and from the deformation we have erosion, and after the erosion we may have sedimentation. Again, these kind of cycles make different kind of geometries and relationship between the geological units. So all the geological map are actually the interactions between the geometries of the geological units and volumes underneath the surface intersecting the topography, so that we have for deposition the classical horizontal deposition with the sedimentation of one unit on top of each other. Then after deformation we may have inclined stratification, and after erosion and deposition again we may have this kind of angular intersections and conformity. So these kind of different geometries, when interact with the contour lines that define the slopes and the topography of a given landscape, give different kind of geometries on the surface, so that we have a kind of complex framework like this one, in which we have a stratigraphic sequence that has been severely deformed with folds, and folds is actually visible or can be actually seen even in perspective view and in planar view. So all these kind of geological contexts are geometry in planar view are actually the reflection of what is happening underneath. So going from the very beginning, the easiest part, if you want, the classical horizontal sequence, we have, for example, Grand Canyon in Arizona, in which we have beautiful horizontal sedimentary sequence, and we can see how they interact with the topography, just see them in planar view. So we have the river incisions, and for this we have the exposure of different terraces and scarp showing the stratifications. And if we want to superpose the contour lines, we see that the stratification is nearly following all the contour lines. This means that when we have horizontal stratification, horizontal contact, we are at the contact follow the contour lines. And this is quite a general, I would say, view. So if you know very well the stratigraphy, and we constrain very well the stratigraphy, it's quite simple to derive geological sections on horizontal contacts, since we see that the horizontal contacts are parallel to the contour lines. And this is, for example, a case here on a geological map in the Earth, in which we see this kind of contacts are almost nearly parallel to the contour lines, and the geological section that has been done from A and B so show the horizontal contact. So it's quite, if you want, easy. You can see where there is a contact and then just draw an horizontal plane. Then we have the vertical contact in the other way around, in which we have that are normally associated to dikes, volcanic intrusions, feeding the magmatism on the surface, for example, or can be associated to stratification that has been tilted, folded, deformed by tectonism. In this case, we can even see vertical contacts in a planetary environment. This is Martin crater on Mars, in which we have vertical stratifications. And also in this case, we can try and see how these contacts behave with respect to the contour lines. And we can put ourselves in planar view from the vertical contacts, and then we can superpose the contour lines. And we see that in this case, the contour doesn't care about the shapes of the contour lines. So the vertical contacts ignore completely the contour lines. So now, if we go in a planetary geological context, we have good news, in particular for some airless small bodies, in which planetary, in which the contacts are normally almost horizontal or slightly inclined. And this is an example, for example, in Chang'e 3 site in Cenozoiums close to Imbrium, in which we have radar sounder measurements that show that this kind of layers here are the contact between the regolith, some lava flow units, and eventually some ejecta, and they almost, I would say, horizontal. So if we translate this on a geological map without having any kind of geophysical method for inferring the subsurface structure of a given planetary body, it's quite simple. And this is an example in Bright 2019, which is well constrained in terms of stratigraphy. You see here the stratigraphy, the different crater degradation classes in these 5 instead of 3. And even the position of the intercrater planes and intermediate plane and smooth planes. So knowing well the geography, it is possible quite easily to make a geological section if we understand the intersection, if we consider the intersection of the geological unit, the topography. And this is, for example, the geological section of this map from Wright et al. 2019, in which we see clear that the ejecta contact have a very gentle sloping contact, so almost horizontal. And we have other kind of contact that actually are infrared and are vertical. So with almost horizontal or quite vertical contact, we are able to make geological section in this kind of environment, considering a morphostratigraphic sequence with well-constrained stratigraphy. And see here, we see all the geological sections. Still, we see some deformations due to the impact. So we are placed actually in which we have no horizontal contact, but almost all of them that we see here are quite horizontal, except very close to the Rachmanian basins, which is here, in which we have some sloping contacts. But I would say, for a morphostratigraphic point of view, we use this kind of philosophy. But actually, we know that there are not only morphostratigraphic maps, there are also maps that are attempting to consider the different color. That means possibly a different composition of the units there. Could be by weathering, but some of these compositions could be even the reflection of a different kind of subsurface stratifications. And this is clearly visible, for example, here in Rembrandt Basin, Mercury, in which we see some craters here, here, and here that are exhuming some material which is blue. So we have this smooth plane, they are volcanic, and this blue material is underneath the volcanic material. And also we see some contact here between two different volcanic events. So we have different kind of layers here that can be probed by craters, using the craters as boreholes, actually. So if we consider not the morphostratigraphic map, but the geostratigraphic map, in which we distinguish or try to distinguish the different layers, even in the subsurface, the geological section is quite different, because we have a kind of deformation, at least on the in correspondence of the crater, where the material underneath was flapped on the rim, for example, or could be exhumed in the peak of the crater. So in this case, as you see here, we have no really horizontal deformations, but in a horizontal contact, but some deformations. But we have, in any case, the possibility to simplify this kind of picture, because we have, in this case, a kind of important vertical exaggeration in order to see and show you this kind of deformation. So considering a no vertical exaggeration, we can easily make maps of the different contacts that are gently dipping to horizontal, in particular in the inner part of the basins. So still considering this horizontal contact, we can go up and making some more higher level of modeling. And this is the case of a 3D explicit modeling. What does it mean? It means that we make different kind of geological sections, and we, with the crater and knowing the thickness, we are able to infer the layer position of the layers of the general envelope, the one that is not so much inclined. From this different geological section, we can interpret 3D planar surface, and from the planar surface, we can create volumes and estimating volumes inside a given basin. This kind of 3D explicit modeling is actually one of the first, is the first for a basin ever in a planetary environment. What about the case in which the orientation of the stratification is variable? I think it's a beautiful example is Comet 67P. On Comet 67P, we have seen at the beginning that it is actually two lobes, as you see here, big lobe here and a small lobe here, and we see different strata with different scarps, so scarp and strata. And if we go in close-up view, we see that these terraces and scarps make a staircase pattern that indicate the possibility to have stratification, actually indicate a stratification. So having a stratification, we can measure it. In a kind of context of minor body like this one, we have to measure it just considering the normal to the terraces, so the normal to the stratifications. So knowing the orientation with the normal to the stratification, it is possible actually again to make cross sections. And this, for example, is a portion of the comet 67P. We see the section here, this is the topography here, and the measurement here. And it's quite easy to understand the geological section, interpretation of the geological section, which is actually the connection between the different orientations of the stratification. So we start here, for example, then we assume the stratification, the orientation of the measurement here, and then here, here, here. And in this way, we have this kind of interpretation that actually is quite well explained, also visible even in this kind of picture of Meyer lobe, in which we see these strata that create envelopes like an onion, as you see here. So if we extrapolate the concept to the whole comet, we were able at that time to make a geological cross-section of a comet itself, discovering that the two lobes were actually made up of two different bodies. Moreover, if we use only the measurement, if we have many measurements, like in the case of comet 67P, we can do what we call a 3D implicit modeling that does not depend from the necessarily from the geological sections, but we can be made directly from the measurement or eventually from the contact behavior in function of the topography. In this case was the measurements. So we may infer a kind of conceptual shape of the stratigraphy, like this case, the case of an onion case, ellipsoidal shape. Then we can fit these solids with the measurements, or with more sophisticated software, we can even consider deformation that we may have had on the stratification during the junction between the two lobes, as you see here. So from the measurements, it's possible to create directly geological sections. And if we have enough measurements, it is even possible to make implicit 3D implicit modeling. And this is actually the only implicit modeling ever done in any kind of planetary bodies except on Earth. So if we go back on a bigger body and we have to consider variable stratifications, in this we have to use another kind of measurements. This is a kind of inclined stratification picture in the Alps, as you see here. To the right, we see the stratifications, and in this case, we have to measure what we call the strike function or its orientation to the north. And the strike is the intersection between the plane of the stratification and an horizontal plane. Perpendicular to the strikes along the maximum inclination line of the strata, we have the dip direction, okay, which is the other measurements that can be done, the dip direction, and finally we can measure the inclination with respect to the horizontal plane. So in this way, knowing this kind of measurements, it is possible to create a geological map, and or in the other way around, we can understand the measurement strata, the orientation on the strata and its inclination in function of the intersections of the different intersection of the contact with respect to the topography. So we have different kinds of relationship between topography and stratification. We have the case in which the strata are dipping, okay, in a positive sense with respect to the slope. And this is the anti-dip slope. Then we have the case in which the stratification is dipping toward the slope with the same orientation of the slope. So in this case, the deep angle is less inclined than the slope, for example, but we may have the same with deep angle at the same versus than the slope, in which the deep angle is more inclined than the slope itself, like in this case. And in this picture, we have even an add-on because we have the anti-slope here. So obviously, if we have a case like this one, in one part we have a deep slope, and in the other slope we have an anti-deep slope of the stratification. Going back to a planetary context, and let's see what happens on Mars, for example, on the sedimentary sequence that can be on Mars. And here it's quite clear that we have similar things. So we have, for example, horizontal stratification up there, you see there. Then we have, in that point, we have anti-deep slope stratifications. And then in the other way, in the other part of the slope, we have a deep slope less inclined than the slope itself. And here in the foreground, we have the deep slope more inclined than the slope itself. And it is even clear here from the picture that we see here that we may have a kind of angular unconformity between this part with the horizontal stratification and this part with inclined stratification. And it is also clear that the stratification is more or less with the same orientation and same inclination from here to the foreground. But the interaction with the topography is different. And so we have anti-deep slope, more inclined, and deep slope, less inclined. So now let's have a look with a relationship with the topography again, looking on the planar view, and afterwards superimposing some topography. And now we can see different portions in the different conditions, so that, for example, we can see there, and we see the stratification is following the contour line, so we have a kind of horizontal stratification. In this case, we have the stratification is cutting the contour lines. So in this case, we have the case of a anti-deep slope, and in this case, the anti-deep slope, in case of anti-deep slope, we have that the contour are cutting the contour lines and are wider than the contour line. How much wider depends from the inclination. So we can see clearly that this is the conditions. So then we may have the case of a slope more inclined than the slope itself. So we may have a condition like this one, in which the stratification is cutting the contour line, but it goes with an opposite shape with respect to the contour line. And how much opposite or how much it could be the curvature in function of the topography. If we maintain the topography constant, depends from the inclination. So it will be more straightforward if the inclination is higher, and more gentle, if you want, if the inclination is lower. Then we have the last case, in which we have the stratification that is less inclined with respect to the topography and the slope, like in this case. And in this case, we have still the stratification that is, and the unit contacts that are transecting the contour lines. But in this case, the contacts are tighter and emphasizing the contour lines. How much they could be emphasized, again, it depends from the inclination. So know the shape of the contacts, it's possible to create, to derive the measurements, stratifications. And in the same way, knowing the measurement of the stratification, it is possible to create, to constrain the contact on a planetary surface. And these kind of concepts are well known since the 19th century. Here we see the different cases, the anti-dip slope, the dip slope more inclined than the lobe itself, and the dip slope less inclined than the itself. And to the right, we see a textbook by Lyell in 1874, Elements of Geology, that show exactly the same thing. So if we apply this kind of principles to kind of planar view, like in this case, in which we are in Pikyang, capping, fold and thrust belt. Here we see clearly some quaternary features like talus deposit and alluvial plain, but here it's more important for me the bedrock. And in the bedrock, we may see a different color and different roughness of the bedrock that allow us to see different units. So we have one unit here with these rough limestones here, and then some sedimentary sequence with different color, 2, 3, 4, and 5. So this is the sequence going from bottom to top in this case. And again, we see that we have that this sequence interrupted here, for example, and also is interrupted here. So it means that we may have faults there and some dragging, some faults related to the faults themselves. But in the same case, we see that this sequence is also repeated here. So the same sequence here is repeated here. And this kind of, I would say, shape of the contact with respect to the topography is saying us that the inclination of the stratification it is toward the north, and this part is over this part. So it means that we must add even some elements like these ones that are fault, thrust faults, compressional faults. So considering the geometry in planar view, and it is possible to make a constrain a geological map actually. And with the geological map and the contact well visible, like in this case, it is even possible to make a geological section. So if you see here a geological section from more or less east-west geological sections, we can make the geological section through the crust. See that, for example, this is the faults that I have shown you before with the repetition of the units, and this part is going up with respect to this part with this compressional behavior. And also we see here that here the repetition is inverted from here to here, so we have a kind of faults. So using the geometry of the contacts and it is possible to infer their prosecution, the subsurface, and in the same time knowing very well the stratigraphy, it's possible to understand if there are holes or faults in your case. So if we go again in planetary geological perspective, here it's a case in Crommelin crater, which is a kind of an unusual crater with the big bulge here inside the crater rim, and this bulge it's much bigger than any kind of central peak. So it's something different. It seems a kind of protruding bulge. So this kind of bulge and this kind of crater has been mapped, and we can see the map and we can overlap the map on top of our DTM, and we see here the map. And here are all the material in blue and green, all the material of the rim or of the jack of a nearby crater, this one. And here in brown, we have the sedimentary sequence, which is in between the bulge and the rim, and then the material in the rims that is constituted by two units. In yellow here, you see the orientation that follow the stratification. So knowing this orientation, it is possible to infer the measurements of the strata themselves that we have taken actually. And these black lines here are showing actually axial planes. So the center of the point, the line of maximum curvature of folds. So we have discovered in this way that around this crater we have several folds, and we were able to understand the measurements of the stratification in terms of strike, dip, and dip angle. In this way, it was possible to make geological sections like these ones, okay, in series, and as well as the case of the Rembrandt basin, it was possible to interpolate these planes all around this sector of the basins and create a 3D model of the stratigraphic sequence itself. And here we see the cutting the stratigraphic sequence through the bulge, a kind of zoom. Actually, still there are some I would say errors in the DTMs, but still we have beautiful case in which we have the topography and we know how it is the sequence and how it is the geometry underneath the surface, even in the case of chromery. And this is a case of explicit modeling, like the Rembrandt basin one. So now I'd like to conclude saying what we have retrieved from this lecture. I would say actually several points. The first one is that the interaction between geological contacts and topography allow to infer the subsurface prosecution of geological units. And this is the main way for understanding and understanding what it is in the subsurface and making geological cross sections. Any geological cross section must strictly follow a clear stratigraphic chronology. So that's why it's so important the next presentation by Monica that will constrain the stratigraphy of a given region on mass for going on with the geological section. Another point is that R-less body is dominated by subhorizontal or slightly inclined contacts, or slightly inclined contact between major units. And this is actually, if real, if we consider a broad view, if we consider vertical exaggerations and the deformation due to the craters, we may have the kind of deformation on the crater to be taken into account during the geological section, but depends a lot on which kind of map you are doing. If you want to constrain very well the subsurface structure, probably it's good to have a geological map that is considering both the morphostratigraphy and the real, I would say, the stratigraphy that is related to, if you want, the different bodies and the different compositions. So one of the major aim in the future for geological mapping is try to integrate the morphology, morphostratigraphy informations together with the spectral ones, for example, or the compositional ones, in order to have such constraint. In any case, if we consider a general view, we know that in case of small bodies, we can infer or suppose horizontal or slightly inclined contacts. As I said, craters can be used as boreholes constraining the subsurface stratigraphy, so we can constrain our geological sections using craters if we have no geophysical prospecting there. Geological sections actually are for any explicit 3D modeling, that they are the only one applicable on Moon and Mercury because of the less predictable shapes of the contacts, because of closure, lateral closure of rejecta, of lava flows, and so forth. So at the moment, I think that the explicit 3D modeling, so the modeling that is based on series of sections, is the best one for this kind of small planetary body. On the other way around, the sedimentary sequence on Mars allow deriving geological section 3D models, well constrained by contacts, attitudes, and strata measurements. This means that on Mars, in principle, we can make implicit 3D models in some locations. However, up to date, the implicit 3D model has been applied only on Earth, a mining company, for example, or oil companies, for example, even with geophysical data, and so with constraining with it with geophysical data, and only on Comet 67P on the other solar system body. As I said, it is possible probably to apply it even for Mars. So with this final, I would say, conclusion, I thank you, all of you, for having listening me, and I want to thank you in particular, Riccardo and Luca, that helped me in even realizing this presentation, which actually take a little bit less than predicted. So I am open to any questions if you have them. Thank you very much for listening.
Thank you, Matteo. And is there any question? I know there were some comments in the chat during the talk. One was that, yeah, comets have layers. That's fascinating. And that was answered already by Luca with some references. There was a question from Scott on a specific unit. I don't know, Scott, if you want to refer to a slide number.
Which is the slide?
And that I don't know. What is the top ice for Cameroon, right?
Okay. Yes, probably went a little bit, you know.
Yeah.
And okay, the units here, actually, the top one are the brown one. Okay, this kind of more, I don't know, this kind of brown, okay, this kind of more reddish brown with respect to this one, and these are the units underneath. You can understand it by, as I said, by the stratification, the orientation of the stratification. All these kind of units that you see here are actually subunits of the chromaline, on the brown one. That should be still, that have still to be identified and mapped on the map itself. And actually we are trying to do it, and but still with the measurement it is possible to see the structures. Okay, so we know that we have this kind of structure with these units on top of the bulge units.
Thank you, Matteo. There was a question that was answered already by Riccardo. I don't know if Riccardo wants to add.
Yeah, so they were asking were the values in the case of chromaline measured in any way or just estimated. So the quick answer is yes, they were measured in this area here. We have actually in most of the crater we're able to reconstruct the CTX DTN from stereo images. That's 18 meters per pixel and 6 meter pixel resolution images, and also we have high-rise DTNs at places at 1 meter resolution. So that means we could see the strata banks outcropping, and we could carefully measure the dip and strike of the layers using the 3 points rule. There are many tools that do that in ArcGIS and also in QGIS that you can basically measure all the attitudes of the strata. And then, for example, in QGIS, we will have a plugin that then project the true dip onto a specific cross-section. And then you can derive your own geologic cross-section. This one will be partially covered during the next lessons. This particular function, however, is quite advanced, and we could do a GMAP community call about that in the next future, dedicated to projecting different strike measurements onto a section. I hope I answered.
Yes, I think so, Riccardo. You are just to say that the resolution of the data was quite enough for understanding very shallow, deep angle, like I think something like 10 degrees, or in some cases even less. And I see that there is another questions here, and it is are you, Hector, are you asking me which is the depth of the layer that has been interpreted underneath the surface?
Yes, I think so. I mean, I can answer that since I did
okay, yes,
the work.
You are the best one.
You have to think about that the vertical exaggeration you're seeing here, it's like 10 times the actual topography, just because this crater is very large. You see it's almost 90 kilometers in diameter. The depth of the layers is up to, let's say, 100 meters, no more. What you see is very, very exaggerated in order to derive the actual shape, but you have to imagine that the topography is much more gentle. With such large craters, the depth versus height ratio is favoring the diameter of the crater. And about the proposed mechanism for that uplift, there are many models. There are people that think that these huge bulges are simply aeolian products. So volcanic ash, dust that are accumulating inside craters during wind circulation of Mars and then compacted, and so on. Other models think that this is a spring deposit, so fluid resurgence from depth, and yes, fluid resurgence, and that basically is oversaturated in sulfates, and they simply create some evaporative layers that are those of the dark brownish material, like here, and also here. And I think Angelo can expand on that because he also did a nice work a few years ago about that. And also other more challenging models think that this is a diapir. So a huge body of salt at depth that very, very slowly, since it's less dense than the basaltic plateau all around the crater, uprise and deform the strata coming towards the surface. So there are many hypotheses. Some are more challenging than others. You have to imagine that this crater is placed in an area where the topographic dichotomy of Mars is very gentle, and there's evidence also of fluid activity inside craters, either resurgence by spring deposits or lake deposits. So it's debated. There are many options, and possibly, I think that none of them is false. They could be interplay one with each other.
I would say
they are not mutually exclusive.
Yes, exactly. I think in particular the last two are not mutually exclusive, because actually when you have an impact and you may think about a salt mass, I would say evaporative mass underneath it, you have a sudden unloading in the place of the impact itself that can trigger the diapirism. But this doesn't mean that it could not be associated with water circulation that has been seen, and so with the spring hypothesis. So these two in particular, these two processes are quite, I would say, are possible to have been developed together. I see that the erosional probability of the wind all around the bulge is not actually really well explaining the elevation of the bulge itself, which is higher than the rims. And even if it is a process that can be there, I think there is, but this is my personal opinion, it is not I would say the one that was responsible of the big mold shaping of the crater itself. I would say that the two hypotheses by the wind and the spring has been already published. The hypothesis about the diaperism was only presented on presentations, and we are going to publish it and open a discussion on it, because this will even be important about the fact all around this place in Arabia Terra we have different kind of craters with bulges, and if the diapir hypothesis is well sustained as we think, in function of the orientation of the stratification that we see there and the deformation that we have seen, it means that we may have some evaporative bodies underneath or buried not far from the Martian dichotomy, which makes sense and can give important hints about the climate variability on Mars through